this module, we will be learning about Earth's atmosphere, its processes, composition, and chemical reactions involved. We will be also learning about gas and how to solve the problems involving around it.
The atmosphere is a mixture of gases that surrounds and protect the Earth from harmful ultraviolet rays from the sun and maintains the temperature of the Earth by a greenhouse effect. Without the atmosphere, there could be no life on Earth. The atmosphere contains the air we breathe, protect life from harmful radiation of the sun, help keeps the planet heat from the sun escaping back into space, and is a major element of the water cycle. Keeps the climate on Earth moderate compared to the other planets. The atmosphere of Earth is divided into several different layers. Troposphere, this is where weather system acquire and this is where we live. Stratosphere, this is where the ozone layer is. Mesosphere, a region where there is a drastic drop of air pressure. Thermosphere, this is where the auroras form. Exosphere, the last layer of the atmosphere. The atmosphere of Earth is composed of nitrogen 78% and oxygen with 21%, with trace amount of water, argon, carbon dioxide, and other gases.
The biggest component of air is nitrogen that comprises around 78% of the air. Nitrogen has many uses. It is essential in plant growth and soil nourishment because it is often used as fertilizers. We need nitrogen in our DNA, and nitrogen interacts with soil and atmosphere via a process called nitrogen cycle. Nitrogen follows a cycle where it travels from atmosphere to the soil, to animals, and back to atmosphere. The nitrogen cycle is a repeating cycle of process which nitrogen moves through both living and non-living things. Nitrogen in the atmosphere falls to the earth by precipitation, such as rain or snow. The nitrogen cycle is the reason why nitrogen is the most abundant gas in the atmosphere. It is a perpetual cycle that affects the atmosphere, the soil, the plants, and us humans. The most important gas in the air is oxygen, that comprises of 21% of the air. It is the most common chemical gas element found on Earth. Oxygen is one of the products of photosynthesis and has critical role in respiration of organism. Oxygen is necessary for the survival of all living things. Argon is a noble gas that is found only 0.9% in the atmosphere, but it is more abundant than any other element. Argon is non-reactive. It is a stable and resists combining with other elements. It is also heavy enough that it tends not to be lost in space. There is a relative abundance of argon that is emitted from Earth compared to other gases. There is abundance of argon because it is a noble gas and it doesn't react with other elements, so it is stay as argon as always.
So we have other gases. First of all, we will tackle carbon dioxide. It is one of the important greenhouse gas that helps trap heat to the atmosphere. Used by plants to produce their food, and microbes, they produce food by carbon dioxide too. This is called photosynthesis. Photosynthesis will be briefly discussed later in presentation. Carbon dioxide is added to the atmosphere by human activities, for example, burning fuels, wood, coal, natural gas, gasoline, and oil. Next, we have methane. It is a greenhouse gas that's similar to the carbon dioxide that traps heat to the atmosphere. An increase of methane is in the atmosphere was recorded due to the agriculture and the gas industry. Methane is important to the electricity generation by burning fuel and gas turbine or steam generator. Compared to the other high carbon fuels like what I said, burning coal and natural fuel, So methane produces less carbon dioxide for each unit heat being released. So we will tackle next is water vapor. Water vapor is also most important greenhouse gas in the atmosphere. It is gaseous form of H2O. So what is evaporation and how water vapor being mold? Evaporation turns liquid water into gas called water vapor. If heat is taken away from water vapor, it condenses. So this is what we call condensation. So condensation turns water vapor into a liquid. If heat is taken away from the liquid water, it freezes to become ice. The water cycle is called hydrological cycle. So water vapor is also part of the water cycle that has significant effect of the water patterns on the earth. So this is my end of my presentation. Thank you.
This is Earth's early atmosphere. The Earth's atmosphere was different back then and developed and changed over time. It doesn't have its atmosphere. There's no ocean and life is not existent. However, the gases from volcanic activities, mainly carbon dioxide, made up Earth's early atmosphere. Volcanoes also produce nitrogen gas, methane, and ammonia. There is obviously a lack of oxygen, which is critical for life to exist. This was the breakdown of Earth's early atmosphere. It was composed of primarily 95% carbon dioxide, 4% water vapor, and 1% of gas traces. To compare, here is the composition of our atmosphere before and today. It is obviously different as oxygen is not present in the early atmosphere. So in the early atmosphere, the blue represent carbon dioxide, red is water vapor, and green is the traces of gases, which is I mentioned above. And from today's atmosphere, it is blue for the nitrogen, which is roughly 78%, and the red for oxygen, which is 21%. Argon, color green, 1%, and the other gases is 1%.
In this topic, we will discuss the decreasing carbon dioxide. As time progressed, oceans began to appear and the temperature of the earth has now cooled down. The carbon dioxide in the air began to react with the water in the ocean, producing sediments that reduce the total carbon dioxide in the atmosphere. Like example nitong dalawang picture na to. So before we proceed, ano nga bang carbon dioxide? So carbon dioxide is a gas consisting of 1 part carbon and 2 oxygen atoms. Ito yung pinaka importanteng gases sa earth dahil ginagamit ito ng mga halaman para makapag-produce ng carbohydrates in process called photosynthesis. Next. So, photosynthesis was a big factor that decreasing the carbon dioxide levels in the earth. So, bago natin i-discuss yung picture na to, ano muna ang photosynthesis? So, photosynthesis is a chemical reaction that takes place inside a plant and producing food for the plant to survive. So, similar to this picture, habang lumalaki ang halaman, nag-absorb siya ng carbon dioxide sa atmosphere at nagpo-produce sila ng glucose bilang kanilang pagkain at oxygen. Then, as plants started to grow, they fed into the carbon dioxide in the atmosphere and produced glucose as their food and oxygen, kagaya ng sinabi ko kanina. So, here's the chemical equation of the photosynthesis process. 6 moles of water and 6 moles carbon dioxide and light as the catalyst will yield 1 mole of glucose and 6 moles of oxygen gas. So that's it for this topic.
So the next topic is about greenhouse gases. So what are greenhouse gases? Greenhouse gases are compound gases that trap heat or long-wave radiation in the atmosphere. Their presence in the atmosphere makes the Earth's surface more warmer. Sunlight or shortwave radiation easily passes through the atmosphere and these gases. This radiation is being absorbed by the surface of the Earth and released as a heat or long-wave radiation. The molecular structure of the greenhouse gases allows them to absorb heat, release or trap them in the atmosphere, and after that, re-emit them back to the Earth's surface. So this heat trapping phenomenon is known as greenhouse effect. So what are the main greenhouse gases? The main greenhouse gases are carbon dioxide, methane, nitrous oxide, and fluorinated gases.
We all know that greenhouse gases are critical in maintaining the Earth's temperature. However, there is an increase of it in the 21st century. The other process which the atmosphere is involved is the CO2-O2 cycle. The CO2 is being taken by plants, then converted to O2 by photosynthesis. Humans and other organisms breathe the O2, then CO2 is released by respiration. However, there is an increase of burning of rainforests that release CO2 in the air and leaving fewer trees to produce O2. The balance of carbon dioxide and oxygen was disrupted by man, leaving negative effects that will also affect us. Also, the use of chlorofluorocarbon, release of methane and car fumes have increased too. The excess greenhouse trap more heat in the earth, making the temperature high.
So for the next topic, I am going to talk about and tackle about the ozone layer. The ozone layer is a region located at the stratosphere, and it is basically composed of ozone, or what we call O3. This ozone blocks 95 to 99% of the ultraviolet radiation that comes from the sun. However, O3 is a very unstable element due to its bent and triatomic structure that can be seen and is actually illustrated with the photo attached in the slide. It is also said that the increase of the chlorofluorocarbons produced have greatly affect our ozone layer. So for today, we are going to tackle about how do these chlorofluorocarbons destroy the ozone layer. So first, the ultraviolet radiation interacts with a CFC molecule, stripping off a chlorine atom. These chlorine atoms strikes on an O3 molecule, resulting in an O2 molecule and a chlorine monoxide molecule. So, due to the instability of the O3 molecule, the stripped off chlorine atom interacts with O3, resulting in an O3 molecule and a chlorine monoxide. So next, a free atom of oxygen collides with the chlorine monoxide. And then lastly, two O2 molecules are formed and the chlorine atom is freed to destroy another O2. So basically, the chlorine atom from the CFC from the chlorofluorocarbons destroy the ozone layer. So this process of the chlorofluorocarbons destroying the ozone layer is basically the main reason of why we have climate change. And we all know that the absence of the ozone layer means that we will be receiving the whole radiation that comes from the sun.
In the graph, we can see the increased trends of the global temperature, which tell us the global warming is really happening. And the climate change effect, it's because of the increase of heat that polar ice caps are melted contribute to the increasing of sea levels. Climate changes. Our climate change is continually changing. There is evidence for this change, for example from fossils, which tell us that certain times the world has been much warmer than it is now. And there was a little ice on the North Pole. There is also evidence to suggest that other times the ice cover was much greater than it is today. For example, weather recordings, ice cores, rocks and fossils. In the weather recordings, they're using thermometers are more accurate now, and digital readings can be recorded remotely. Ice in the ice cores, look Locked inside ice are molecules and trapped air which are preserved year on year with more snowfall. Subtle changes in temperature can be measured from ice cores extracted in Antarctica. In rocks and fossils, this can be studied for information covering longer time periods. For instance, limestone found in Yorkshire would have been formed on the bottom of the warm seabed millions of years ago.
So, in this topic, we can classify the excess greenhouse gases and other negative contributors to the atmosphere as atmospheric pollutants. Atmospheric pollutants includes fuel source and combustion reactions such as coal, fossil fuels, and petroleum. One of the major contributors to atmospheric pollution is carbon dioxide emission. The use of coals, petroleums, and fossil fuels are the main source of carbon dioxide emission. Also, factories use these fuels as a source of energy. There are also other atmospheric pollutants that harms not only the atmosphere but also other organisms. So, next one is, these are the other types of atmospheric pollutants. First, carbon monoxide. Carbon monoxide is a toxic gas. It is colorless and odorless, and so it is not easily detected. Carbon monoxide is commonly produced in burning of fuel in cars, engines, and stove for cooking. Next is sulfur dioxide. Sulfur dioxide, or SO2, and oxide of nitrogen can cause respiratory problems in humans and cause acid rain. So, SO2 is produced in burning of fossil fuels, which powers up factories and facilities.
Ammonia. It is commonly used in agriculture. It can react with other pollutants that can be harmful to the ecosystem as it cycles in the atmosphere. As it was discussed earlier, ammonia is part of the nitrogen cycle which interacts with the atmosphere, the soil, and the plants. Overdosing of ammonia can damage not only the plants but also it will be toxic to breathe. How do we reduce our use of pollutants and our carbon footprint? Number 1. Use of renewable and clean energy. Using this kind of energy such as hydroelectric, wind, and solar can eliminate the use of non-renewable energy such as fossil fuel that contribute to the carbon dioxide emissions. Number 2. Reuse, reduce, and recycle. Recycling rather than buying new stuffs enables us to lessen our carbon footprint, which means that we contribute less negative effects for the environment. Number 3. Driving less. Our vehicles' gasoline produce a large amount of carbon dioxide in the air. Riding a bike, walking, or jogging can lessen the carbon dioxide emissions and also help you exercise.
Good day! In this part, we will be discussing the laws and components of the third phase or state of matter named gas. We will be taking a good look, or probably just a review of the different gas laws since they were already discussed during our junior high school. First, in order to understand the gas laws, let's define what gas is. Gas is a state of matter that has no fixed shape and no fixed volume. It has a lower density than any other states of matter. So why is it important to learn more about the third state of matter? It is because the study of gases allows us to understand the behavior of matter at its simplest, such as its individual particles and the interferences between each of them. Next are some of the units or variables that we need to remember. First, we have pressure. Pressure is the exerting force that the gas particles exert in the interior volumes of a container. For the units, we have atmospheres or ATM, pounds per square inch or PSI, millimeters of mercury or mmHg, and pascals or Pa. For the conversion factors, we have 1 ATM, which is equivalent to the following: 14.7 pounds per square inch, 760 millimeters of mercury, and 101.3 kilopascals. For the temperature, we have the unit Kelvin. 1 Kelvin is equivalent to 273.15 degrees Celsius. For the volume, we have the unit liters. For the number of molecules, we have the unit mole. And last, for the standard temperature and pressure, we have negative 32 degrees Celsius or 273.15 Kelvin at 1 atmosphere.
The first law was named after Robert Boyle or Boyle's law. In here, we have an inverse relationship between volume and pressure, and the temperature increases. Inverse relationship meaning if the volume increase, the pressure decrease, or vice versa. For its formula, initial pressure multiplied to the initial volume is equal to the final pressure multiplied to the final volume. So a sample of helium gas in a balloon is compressed from 4 liters to 2.5 at constant temperature. If the initial pressure was 3 atmosphere at 4 liters, what is the new pressure at 2.5 liters? So algebraically, we can manipulate the equation to meet the demands of the problem. So the initial pressure multiplied to the initial volume all over the final volume, substitution, 3 atmosphere times 4 liter all over 2.5 liter, we will have a final answer of 4.8 atmosphere. So the application of Boyle's law is if we press down or squeeze a balloon, the container of the balloon decreases and the pressure inside increases. Then, if the balloon cannot hold it anymore, it will pop. The second law is named after Jack Charles or Charles' law. We have a direct relationship here between the volume and temperature, and the pressure is constant. So, if the volume increases, the temperature also increases or vice versa. The formula would be initial volume multiplied to the final temperature is equal to the final volume multiplied to the initial temperature. So a container has 600 milliliters of air at 300 Kelvin. What is the volume at 333 Kelvin? So again, manipulating algebraically the equation given or the formula given, then substitution, 600 milliliters times 335 Kelvin all over 300 Kelvin, cancellation of like terms or Kelvin, we will arrive at a final answer of 600 milliliters, and we can also convert this to liter. So for us to appreciate the concept in the Charles law, it can be seen in an hot air balloon. So in hot air balloon, the air inside the balloon or the air in the hot air balloon will have an increased temperature. The net weight of the balloon plus the hot air is less than the weight of the equivalent volume of cold air. Then, the balloon will start to rise. The next law is Gay-Lussac law. It was named after Gay-Lussac. So, in here, we have a constant volume, and the pressure and temperature have a direct relationship. Meaning, if the pressure increases, the temperature will also increase, or vice versa. The formula would be initial pressure multiplied to the final temperature is equal to final pressure multiplied to initial temperature. So what is the pressure of confined gas with an original pressure of 3 atm and a temperature of 200 Kelvin if the temperature increased to 1000 degrees Celsius? So we will add to the initial temperature we will add 273 Kelvin. Therefore, 3 liters multiplied to 1273 Kelvin all over 200 Kelvin. Cancellation of like terms, we will arrive at a final answer of 19.1 atm or atmosphere. So for the last application of Gay-Lussac law, it can be seen on our home, or it can be applied to pressure cooker. So in pressure cooker, it is used to tenderize a meat or mga pagkain natin na pwedeng palambutin. So inside a pressure cooker, there is a water. If the temperature of the water increases, there will be an increase in water vapor. Then, hindi naman magbabago yung cylinder or hindi mag-expand yung material. So, mako-contain yung pressure sa loob, dadami din yung pressure, and mapapalambot nito yung meat or yung mga pagkain na nilalagay natin sa pressure cooker.
The next gas law is the Avogadro's law. It is named after Amedeo Avogadro, which we are familiar of because of the Avogadro's number. It states that the volume of a gas is directly proportional to the number of moles at constant temperature and pressure. Its formula is V1N2 is equal to V2N1. For example, a sample of 0.15 moles of gas has a volume of 2.5 liters. What is the mole of the sample if the volume is increased by 9.2 liters? So the formula is V1N2 is equal to V2N1. We will derive the formula by using algebra. So our formula will be N2 is equal to V2N1 over V1. We will plot the values at the formula. It will be N2 is equal to 9.2 liters times 0.15 moles over 2.5 liters. We'll do multiplication. It will be 1.38 mole liter all over 2.5 liter. And by dividing it, our answer will be 0.55. The next one is the combined gas law. This is where the principles of Boyle's, Charles, and Gay-Lussac's law are applied. Its formula is P1 V1 T2 is equal to P2 V2 T1. For an example, the volume of a gas-filled balloon is at 30 liters at 313 Kelvin and 1.75 atmosphere pressure. What is the temperature of the balloon when the pressure is at standard and its volume is at 50 liters? We will again derive the formula P1 V1 T2 is equal to P2 V2 T1 because we are getting the temperature, second temperature. So our formula now will be T2 is equal to P2 V2 T1 all over P1 V1. We will plot again the values under the equation. So it will be 1 ATM times 50 liters times 313 Kelvin all over 1.75 atmosphere times 30 liters. So it will be, by using multiplication, it will be 15,650 liter Kelvin atmosphere all over 52.5 atmosphere liter. So we will divide it and cancel the other units. We will be getting 298.1 Kelvin. It is the second temperature of the equation. The last gas law that we will talk about is the ideal gas law. It states that the pressure, temperature, and volume of a gas are related to each other. Its formula is PV is equal to nRT. We will notice that there's a new variable, which is R. R is the universal gas constant, which is equal to 0.8206 liter atmosphere over K mole. For an example, determine the volume occupied by 2.34 grams of carbon dioxide gas at STP. We are tasked to find the volume in the equation, so we will be deriving again the formula PV equals nRT. Now, the formula will be V is equal to nRT over P. So, before we will plot our values, we need the mole of the equation. The 2.34 grams of carbon dioxide gas will be divided by 44 gram per mole, which is its molar mass. So, we all now have the values, so we will be substituting them. Okay, V is equal to 0.05 mole times 0.08206 liter atmosphere over K mole times 273 Kelvin all over 1 ATM. Then we will do multiplication and division. The answer will be the volume is equal to 1.19 liters. This is the volume of the equation.